Hi class, welcome back. So today we're gonna go and introduce section 4.2. In this section we'll talk about exponential and natural exponential functions, in particular into what we call a compounding function. So we'll introduce first the exponential function, and then we'll have a few problems where we discuss the compounding part. Alright, so let's begin. What is an exponential function? Well, exponential function is a function that is in the form of an exponent, right? In other words, the variable is the exponent. So often we use this for when we're talking about a problem that it regards an exponential growth or decay function. So an exponential growth or decay function is a function that grows or shrinks at a constant percentage growth rate. The equation can be written in the form of, and if you notice here, we have a constant, just a constant that we have that constant, and then it's growing at this form, right? You have a value here. This is the rate, and then it's being exponential, right? The basic form of this, an exponential function, is in this form, right? This is the exponential part, and this is just obviously to generalize it. It could have a constant in front of it. So in other words, in this, if you compare these two, it will be the case where this is your b, right? Because it happens to be a constant. A tends to be the initial or starting value of the function, and then r is the percentage growth or decay rate, which is written as a decimal, fraction decimal, right? B is the growth factor or the growth multiplier. Since powers of negative numbers behave strangely, we will limit b to be positive value. So we'll assume that b is always positive, and that's pretty much it, right? So that's how we're gonna be using this in a particular problem called compounding interest, and we're gonna transition to an example here. So here we're gonna try to kind of derive this special formula for compounding problems. So so be patient with me in this problem in this video, because I'm gonna show you guys where the formula that we're gonna be using in the next videos came from, right? So a special type of exponential function appears frequently in real-world applications. To describe it, consider the following example of exponential growth, which arises by compounding interest in a saving account. Right. So suppose a person invests P dollars in a saving account with an annual interest rate R, and which is compounded annually. The amount of money after 1 year is. So what I mean by compounded is, if you think about it, it's kind of like it's subdivided, but it's applied that many times. So in other words, this rate is being applied annually. So every year you apply that interest, right? The amount of money. So if we think about the amount of money after 1 year is going to be, right. So this is the amount of money after one year is going to be the initial amount that you started with, your investment, right? Because your investment is going to be in the account, right? So your original investment plus you're going to add a percentage of the investment, right? In other words, how much interest you generated, right? So you're going to multiply these two, right? And these two will give you a percentage back from your investment. You add these two together, and or you can think about it as being like you factor p out, then you're left with the principal times 1 plus r, right? Plus your rate. Right. So that's 1 year. But let's think about what happens if you do this for 2 years. So if you do this for 2 years, what's going to happen is you're going to have the amount of money from the previous year, right? How much you generated the previous year, which is this, right? This is the total amount of money that you have last year, which is includes the principal plus whatever interest you earned. And then so that the amount you earn, and the amount of money you have in your account from last year, plus a percentage, right? The interest rate generated from the amount you had last year, right? So what happens is that since you have a bigger amount in your account from last year, you're gonna take a percentage, right, of the investment, right? Sorry, you're gonna an interest. You're gonna gain some interest from the amount you generated from last year, and that's the amount right here. And if we convert this back in terms of p, well, this is this, right? And then this one is the same way, right? That's right there. And then the r is right there, right? And if you think about it, you can factor out the the p and the you can factor out the p and the p times 1 plus r, and then you're gonna have p and factor that p plus 1 plus r, and you're gonna be left with, actually I'll have it here, 1 plus r times 1 plus r. Let me try that again. P times 1 plus r times 1 plus r. If you notice, that's what you're going to be left out. But if you think about it, this is the same base, so that could be the same thing as 1 plus r squared. And that's what we have here. So what we're saying here is that the amount of money at the end of 2 years is going to be equivalent to this. If you think about it, what we're trying to gain from here is see a pattern, and the pattern is that at 2 years, when you have 2 years, that's going to be sort of almost equivalent to what the power will be. So we can generalize this by saying the amount of money you can have at some random year t can be described as p times 1 plus r to the power of t, right? So we don't have to do this over again. You can kind of think about that this is gonna be our function, but we're not done yet, right? We need to think about, well, what happens if we compound this more within 1 year? And here's an example. Let's say you compounded this investment twice per year, right? Twice per year. So how much is this gonna happen, right? So what we're gonna do here, in order for us to compound this twice a year, what we need to do is we're gonna take the rate of interest, we're gonna divide it by 2, right? And that's gonna be the first the first the first time your interest rate will be applied. But you don't have to wait a whole year. You can just do it half a year, right, for this amount to be applied. So that's what we're saying here. So you have your principal plus half of the rate times your principal, right? And that's gonna be 1 period, right? And if you factor p, then you're left with this. If you, to complete the entire year, right, to complete 1 year, we would do it again, right? To be when t equals 1, it'll be the amount you generate in the first half of the year plus how much you're gonna generate the second half of the year, right? So it will be the same thing, another half of the interest rate times how much you have now in your account, which is a 1/2. And then if you compare this back into p's, you end up getting this p, and then this also be this p right here. By doing this, we can factor out the p plus 1 r over 2, and you're left with 1 plus r over 2, which is going to be the same thing as this. And so you end up getting p times 1 plus r over 2. So if you notice, the number of compounds in within 1 year happens to be the same number of exponent. But wait a minute, didn't we say that in general that would have been the number of years? But now we're saying that this is going to be the compounding. That actually fits all together. If you generalize this to number of years, what we're going to do here is we're going to have the same equation, right? R over 2. But now what we're going to do is we're going to multiply the compound number of periods times the number of years. In general, we're going to say that the if you're going to compound your money n times per year, n times per year, then the amount of money in the account after t years will be p times 1 plus r over the number of times it's compounding per year, raised to the power of number of times is compounded per year times the number of years. So that is actually the equation, one of the most important equations that we're going to be using in this section. And it's right here. The last one here, what we're going to do is, well, what happens if we ended up doing this continuously. So let's say we decide that we can compound this at a continuous moment, right? Meaning that you're not waiting for any specific day to compound this, but you're saying that is compounding without stopping. That means that in this case, the number of periods you're gonna have is going to be infinity, right? And so we did some algebra manipulation here in this problem, and we could manipulate this using m equals n over r, and we can transform this into this equation, and then take the limit as n goes to m goes to infinity. This actually gives us this exponential rate. So when we think about continuously, is going to give us as another special type of compound problem, where the formula will be equivalent to p times e to the r of t. So this connects to what we talked about in the last section about regarding the exponential function. So in the next chart here, we're going to briefly summarize the way we're going to use these formulas. So when we think about compound interest, we're going to have two types of problems. One that is compounded in periods, and one that is and then one that is compounding continuously. So if a principal amount of money P is invested in an annual interest rate R, and it is compounded n times per year, the amount of money in the account after t years is going to be given by the natural function, not natural function, but by the function, um, P times 1 plus R over n raised to the nt. Um, and then AFT, where AFT is known as the future value after t years, where P is the principal, R is the rate, N is the number of times is being compounded, and T is the number of years. And so here, the way you're gonna see it in word problems will be the following. You're gonna see the word compounded followed by one of these labels. So to determine N, you must count the number of compounding periods per year. What do I mean by that? For example, if you are given a problem that is compounded annually means 1 year, so the period is 1 year. Then you have to ask yourself, how many periods of annuals are in 1 year? Well, that's kind of straightforward, right? There's only 1 year in 1 year. If I give you what is if it's compounded semi-annually, semi-annually is what we call like half a year. So there is how many periods of half of years are in 1 year? Well, there is two of them, right? So there's two periods. Compounded quarterly, that almost kind of gives it away, right? There's 4 quarters in a year. Compounded monthly, that means that there's 12 periods of a month in a year. And weekly, compounded weekly, that implies that there is 52 weeks in a year. And if it's compounded daily, then your n is going to be 365, because there's 365 days in a year. So this is how we're going to describe the compound component. If the money P in the annual interest rate R is compounded continuously, right? You're going to see the word continuously. The amount of money in the account after t years is going to be given by the natural exponential function AFT equals P times e to the power of R times t. And so that's it, right? So we can clearly see the distinction between both of them. If you're given any of these, you're going to be using this function, because obviously we need an n there, right? When you're talking about compound continuously, you don't need an n, because the function will be a natural exponential function. And then lastly, we're also going to talk about a special type of annual percentage. We can measure the annual percentage when it's being compounded. So if I ask you, what is the annual percentage rate that is given after the compounding in the years? So that means that what is the reflection of the rate after you compounded your account, right? Because this is generating more money as you compound it more. The real rate is not going to be the same, right? This rate is not going to be the same rate as the rate R. So to find the annual percentage yield, APY, is you're going to do it by almost using the same function, right? It's the same function, except what we're going to do is 1 plus R over N raised to the N, no T there, and then minus 1. So that will give us the effective annual percentage rate, right? What's actually the rate that you're actually generating every year. Anyways,